Hi, welcome to Elasticity. Today, as you can see, we are going to talk about the statement of the boundary value problem for homogeneous isotropic Hookean bodies. So, if you remember, we had the three stages of our reasoning process. One was the real world, one was the interface world, and one was the mathematical or the symbolic world or the virtual world. And we are now looking at converting all the questions about elasticity into symbolic representation. That's where we are. Okay. So, in order to do that, we are going to start with this statement of the boundary value problem for homogeneous isotropic elasticity. Okay. So, let's start with the input data. What is it that we need to know before we can start the problem? The first thing is I need the body description. What does a body look like? And essentially speaking, we have the following setup. We have, this is the interior of the body, and it is given by these functions being less than 0. So boundary is not included. We'll have to deal with the boundary separately. Okay, and I've drawn the body like sectional so that it's easy, but it doesn't have to be. Then inside the body, I have to be given the elastic moduli. Either for an anisotropic body, you have to give me the SIJKL or CIJKL, or E and nu. And if it is anisotropic, you have to give SIJKL. If it is isotropic, it's enough to give two values, Young's modulus and Poisson's ratio, or shear modulus and Poisson's ratio. And you have to give it at every location. If it is homogeneous, that means the value of E and nu are the same everywhere. Okay, that's what we mean by a homogeneous body. Then I have to give body force field. Can you see that? It's like forces acting on the body. This is action at a distance. Cannot be something that has to do with contact. It has to do with action at a distance. Okay, very good. Then I have described the interior. Now I have to describe the boundary. This is where the real challenges are. So boundary description starts out, there is my body, and the boundary is divided into 4 pieces. Okay. The traction boundary conditions, which is called partial omega traction, is where I specify non-zero forces per unit area on that surface. Displacement boundary condition, where I specify a displacement. Mixed boundary conditions, where I specify normal displacement and sideways traction. This is actually friction boundary condition. And the last one is free, which is my default. That is, if I don't specify anything, that means traction is 0 on that surface. Okay. So first up is traction boundary condition, and the condition says the stress times normal, outward normal. So normal is like that. Stress times normal must be equal to traction, which is known. Okay, and there, that this is partial omega traction, this is partial omega traction. Okay, it doesn't have to be contiguous. It's just that some portion of the boundary traction is specified. Okay, then another portion of the boundary displacement is specified, u equal to u star, partial omega u, partial omega displacement. Okay, in this it looks like the displacement is fixed, but that's not what we mean. It means it's specified. That's all. You can say I'm going to pull it by a distance of 0.01 inches, and that's perfectly fine. Okay. Then you got the mixed boundary condition, which looks like rollers. Okay. That means I know the normal displacement and the tangential traction. In many cases, for roller type conditions, the tangential traction will be 0. And the last one will be default, which is all of this. This is partial omega mixed, and this is partial omega free. Make sense to you? So these are our boundary conditions. So this is what you have to give as input data. Now let's see what we need. Output and requirements. We will land up with 9 coupled first order partial differential equations. That's what we're going to end up with. Let us see what they are. We need to find the stress field and the displacement. So stress field is 6 components of stress, displacement is 3, that's what gives me 9. Okay, so what does the stress have to satisfy? They have to satisfy balance laws, that gives me this, right? Actually only this gives me 3 equations. I need 6 more that come from the material response function. Material response function is for a Hookean material, it looks like this: 2 times strain equals the compliance times stress, and the 2 is because of the fact that I want to write it in terms of displacement, ui comma j plus uj comma I. If I write stress in terms of displacements, then it's actually quite nice, and it'll be an exercise for you to see what happens to the ul comma k term. How come I wrote only uk comma l? So this is 6 equations. So 6 plus 3 is the 9 coupled PDEs. For isotropic materials, we can write it in many different ways because we are going to use it in every way. We got to make sure we understand. For isotropic material, shear modulus is E over 1 plus nu, where nu is Poisson's ratio. This is shear modulus. And one way to write it is in terms of sigma and in terms of displace, 2 times the strain in terms of stress, that's that, which I can write it in direct notation. This is gradient of u, ui comma j, uj comma I is gradient of u transpose equals 2 over E 1 plus nu times sigma minus nu trace of sigma I. Okay. Trace of sigma means sigma 1 1 plus sigma 2 2 plus sigma 3 3. I can also write it solve this for sigma in terms of epsilon, in terms of gradient of u, and it looks like this. You will get a new constant called lambda, which is this messy constant. I'm just solving. This is a set of linear equations, no? So I'll solve it and I'll get this, which looks like this. This is our most useful form. It looks like sigma equals mu times gradient of u plus gradient of u transpose plus 2 nu over 1 minus 2 nu divergence of u. You will see bad things will happen when nu becomes half. So be very careful with all of this, because when nu becomes half, things go very bad. Okay. So this is our set of 9 equations. I have to solve the equations of equilibrium and the material response function, which is here, together with the boundary conditions. If I solve this, I'll find the solution. So let us look at the displacement formulation. What we do is, instead of solving for 9 first order differential equations, we are going to eliminate the stress, because we can write it in terms of the displacements. So you will land up with, so let me write it down, eliminate sigma in favor of gradient of u. You know what I mean? Sigma is a function of gradient of u. If I do that, I will find that this nice looking equation is what I have to solve. This is 3 equations for 3 unknowns. Where did I pay the price? Notice that there is a gradient of u. This is first order, and then there is a divergence. This is second order. So 3 second order differential equations for 3 unknowns. For homogeneous materials, if I substitute for C, I will get this messy looking equation. Gradient of divergence of u. Remember, divergence of u is a scalar. So gradient of the scalar plus 1 minus 2 nu divergence of gradient of u. So notice grad div u plus 1 minus 2 nu div grad u plus 1 minus 2 nu over mu body force equal to 0. And if body force is gone, if this is equal to 0, then you will see that my displacement differential equation depends only upon Poisson's ratio. So I want you to understand, actually the most important parameter for elastic materials is Poisson's ratio. It's not so much modulus, because modulus will become just only a scaling factor. It's the Poisson's ratio which actually determines a lot of the features of differences between materials, one material to the other. Okay, so this is a very interesting thing, and you may not have thought about it, but we will talk about it a little bit more later. Okay, this gives us 3 coupled second order partial differential equations together with the boundary conditions. And just to make sure we know what the boundary conditions are, I'm going to go all the way back. There you go. Boundary conditions are traction, displacement, this, and default. So if you set this up, you now have converted the entire physics problem into an entire mathematics problem. With that, we are done.